Good morning. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. Today we are going to talk about imperfect columns. In particular, we'll talk about residual stresses and its effect on column design curves. We started with spring bar models, which is perfectly straight. Then we moved to Euler columns, which again is also perfectly straight. From Euler columns, we also studied columns with practical boundary conditions. Again, we assume the column to be perfectly straight. From there, we moved on to column theories, where the buckling of stocky short columns which are perfectly straight must be determined by considering the inelastic behavior. We covered tangent modulus theory, double modulus theory, and chain-lace theory. Again, the assumption here is perfectly straight columns. However, straight columns do not exist in actual engineering structures. So there are two types of columns. One is the initially crooked column or a bent column, which is dealt by Perry's formula. The other one is also known as eccentrically loaded columns, which is dealt by secant formula. Both these derivations were seen in the last class. This we call it as imperfection in geometry. So what is imperfection? It is the deviation from ideal column condition. So we have solved the problems with initially bent shape of the column. These are all geometric imperfections at the member level and can be solved using Perry's formula as well as secant's formula. However, we need to understand that imperfections can also be within the material at the cross-section level, which are called material imperfections. Typically, material imperfections arises during manufacturing and fabrication process, leading to residual stresses. Whereas geometric imperfections arises during transportation, handling and erection process, also known as initial out of straightness. Now let's look at how hot rolled steel sections are manufactured. Hot rolled steel sections are manufactured from molten steel. From molten steel, it is formed into billets. As you can see here, the billets are in red hot condition. Basically, it is malleable at this stage. The billets are rolled through a series of rollers. The rollers actually produce the desired shape. From the desired shape, we can get our eye sections, channel sections or angle sections, as you can see from the right hand side. The uneven heating and cooling process introduces locked-in residual stresses in the cross-section. Now let's talk about residual stresses. Here is the stress versus slenderness ratio curve, which is the typical Euler curve. The x-axis is scaled by R, which is the effective slenderness ratio, and the y-axis is sigma. When sigma reaches sigma naught, or when KL by R reaches a critical value, we reach sigma naught, which is the onset of yielding. The point at which onset of yielding starts can be defined as yielding versus elastic buckling. To the right, we have elastic buckling, which are slender columns. To the left, it is yielding, which is a stocky column. However, we do not get a perfect straight line and then a curve. As you can see here, the practical test column results indicates there is a deviation between the curves. So the practical test columns indicate that the strength of the curves are not very high in the practical range. The practical range is the range where most of the columns are designed. It is neither slender nor stocky. The practical column basically is in the inelastic zone, where the failure is due to yielding and buckling happening simultaneously, which is also known as inelastic buckling. So what is the reasons for the difference in the behavior of a practical column? The answer is imperfections. Column strength is significantly affected by two types of imperfections. They are residual stresses and initial out of straightness. Let us understand the causes of residual stresses from the following topics. The first topic is restrained bar model. The second one is welding of plates. The third one is a hot roll section. What you see here is a restrained bar model. Basically, it is a bar which is restrained at both ends. When we heat the bar uniformly, the bar tends to expand, which means that during expansion, there is a stress buildup and it happens until T is less than T naught. T naught is the critical temperature. Say, for example, T naught is equal to 100 degrees Celsius. There is expansion until it reaches 100 degrees Celsius and there is a stress buildup. However, when T exceeds T naught, the yield stresses begins to drop and yielding starts to happen, and then there is a stress relieving that happens in the member. This leads to a stress-free condition. However, when we start to cool the same member with restrained ends at both sides, there is contraction and there is an increase in sigma y. Basically, when we cool it, it regains its strength, but it is only up to T greater than T naught. However, when T is less than T naught, the end conditions prevent free contraction, which leads to buildup of stresses. However, in unrestrained bars, there will be no residual stresses. Let's talk about welded plate. When we weld two plates together, we have some kind of a heat that is being applied to create fusion. Based on fusion, the welding takes place. The heat leads to expansion of the material. During the process of cooling, after welding, there is a contraction. So, the softened T less than T naught material restrains free contraction of the formerly molten/softened T greater than T naught material, thereby inducing tensile stresses in the later. This locked-in tension force must be balanced by a compressive reaction since there is no externally applied force, resulting in the typical CTC pattern. C here stands for compression, T stands for tension. So the edges of the flanges here are experiencing compression, where there is a heat applied, there is a coagulation of material, there is a tension that is applied at the center. Now let's look at hot roller section. So when we have a hot roller steel section, when the initial temperature is greater than T naught and there is uneven cooling, we have different zones which experience different residual stresses. As you can see, the edges of the flanges at the top as well as the edges of the flanges at the bottom are designated as A. The flange web junction is designated as B, and the center of the section is designated as C. So when we heat the material greater than T naught and when there is uneven cooling, the cooling of the zones A is exposed more and it is faster than zones B and C. Hence, toes of a rolled I section tends to be in compression. As you can see here, you have this kind of a residual stress distribution where the edges of the flanges are subjected to a compressive force whose magnitude is equal to 0.3 sigma y, and at the web flange juncture there is 0.3 sigma y, which is tensile in nature, and again on the right side of the flange edge you have 0.3 sigma y. This is the typical residual stress pattern that can be experienced in a hot rolled steel section. And at the web again you have TCT, where the edge or the starting point of the web is subjected to tension, and at the center it is subjected to compression followed by tension at the down. So we need to understand that the residual stresses are always under self-equilibrium condition, which means that the integral of compressive force, integral of sigma c into dA, is equal to the integral of sigma t into dA, which is equal to the tensile force. So based on a large number of experimental investigations, it has been concluded that the average value of the maximum compressive residual stresses in hot rolled wide flange shapes of moderate strength steels at the tip of the flange is approximately equal to 30% of your yield strength. This is based on the research carried out by Tall and Beadle at Lehigh University, whose publication is shown at the bottom of the slide. How are these residual stresses confirmed from experiments? So the presence of residual stresses in structural steel columns has been confirmed experimentally using both method of sectioning and average stress strain curves obtained from stub column tests. So the method of sectioning is basically very simple. You take a small piece of section that you think is being subjected to residual stresses, and we need to slice it into number of longitudinal strips. Prior to that, you need to put gauge holes at the locations, and then you section the material. After sectioning the material, you have to put additional gauge holes and you have to slice the material as shown in the picture. The length of each strip is measured before and after cutting. The changes in the length are indicative of the residual stresses present in the original member. The next one is the axial compression test on stub or short columns, which exhibit premature yielding due to residual stress. When we subject a subcolumn to axial compressive force as shown here, Two scenarios are possible, one without residual stresses and with residual stresses. First, let us look at the scenario without residual stresses. So when P equal to 0, there is no residual stress pattern. It is simply 0 here. The applied load is 0, P equal to 0. So there are no existing residual stresses. With increment in P, we can see that there is a gradual increase in the stress capacity. When the applied load P is equal to P sub P, which is the proportional limit of the load, the stress increases to sigma sub P, which is the proportional stress. When P equal to P sub Y, which means that it has reached the yield load, the stresses corresponding to that is equal to sigma Y, which is the yield stress. So when we plot the stress versus strain, we get a bilinear stress strain curve, as you can see from here. Now let us look at the condition with residual stresses. To begin with, even before applying a single kilonewton of force, you have a residual stress pattern where there is compression on both edges of the flanges and tension at the center. This magnitude is represented by sigma R, which is typically 30% of your yield stress. Now, when you apply the load, which is the axial compressive load, the compression stresses at the edges keep increasing and the tensile stresses at the center decreases and it touches 0 now. And then again, you keep increasing the load, all of them now experiencing compressive stresses. Now, when sigma reaches sigma sub P, which is the onset of yielding, you can see a curve where there is a huge amount of stresses at the edges of the flanges. And then when you further increase the load, you have reached sigma sub Y. However, the flanges at the corners or the edges of flanges have already exceeded the yield stress. As you can see, they have exceeded the yield stress at the left and right side of the cross section. This, when it is plotted, you have a straight line here up to the proportional limit, which is shown in dotted lines, red color dotted lines. Once it reaches the sigma sub P, there is a deviation in the stress strain plot, and this deviation is as a result of residual stresses, and finally it reaches sigma sub Y and merges with the green color curve that you can see on the right side. So the sigma sub P is the proportional limit, and the difference between sigma sub P and the sigma sub Y is given as sigma P equal to sigma Y minus sigma R. And sigma R is the residual stresses, sigma Y is the yield stresses, sigma P is the proportional stress. So this can again be studied by having a flange where the edges of the flanges have yielded, which is shown in the dark blue color on the top flange as well as at the bottom flange, and the center portion, which is hashed in the between the edges of the flanges, is the portion that has not yet yielded. And you can see here, prior to application of load P by A, there is sigma sub R equal to 0.3 Y. The X represents the major axis bending. And when we apply the load here, we applied 50% of the load here. So when we apply 50% of the yield stress, you have 0.3 sigma Y plus 0.y reaches 0.8 sigma Y, as you can see here on the plot on the right side. We continue to apply the load. Now we have 0.7 sigma Y. When we have 0.7 sigma Y, we have reached the sigma Y at the corners because the corners already have a residual stresses of 30% yield, which is 0.3 sigma Y. So until this point, you can see that there is no deviation in the stress strain plot. It merges with the previous residual stress distribution, similar to the one that is experienced for stress strain curve without residual stress. Now, when we apply further load, we have applied P by A equal to 0.8 sigma Y. You can see that there is a small deviation in the stress strain plot, which is shown in the red color plot here. The dotted line actually deviates away from the bilinear curve slightly. You continue to apply the load and then it deviates further and then finally merges with the green color curve, as you can see here. The distance between sigma sub P and sigma sub Y is given as sigma sub R, and sigma sub R again is the residual stress magnitude. And final stress distribution is shown on the right hand side, where P by A equal to sigma Y, and you have this residual stress distribution shown here, and sigma P equal to sigma Y minus sigma R. So basically, yielding commences at the flange tips when the average applied stress P by A plus the residual stresses sigma R at these points is equal to the yield strength sigma Y of the material. Now, you have this residual stress pattern, which is actually parabolic in nature, and this can be approximated in a linear fashion where one triangle is on the left side and another triangle is on the right side. It's two smaller triangles, and then there is a one big triangle at the center. Basically, the forces should be equal, so the center triangle is double the size of the triangles at the edges. The edge triangles are compressive in nature. The triangle at the center is basically tensile in nature. So when you apply the load here, again P by A equal to 0.5 sigma y, you can see that it reaches 0.8 sigma y at the edges. You apply 0.7 sigma y, then the yielding starts to commence at the flange edges. Then when you apply more than that, the yielding spreads to the inner portions. As you can see here, the spread of yielding at 0.8 sigma y. When you completely load with P by A equal to sigma y, complete yielding takes place across the flanges. Again, this is a plot that we saw in the last slide, again represented here for clarity purpose. Now, column curves which allow for the weakening effect of residual stresses can be produced by using the tangent modulus theory based on stress strain curves from stub column test. So you have a stub column test where you have the stress strain plot. The sigma naught represents the proportional limit and sigma y is the yield point. And when we represent it in terms of the Young's modulus as well as the stress, the Young's modulus in the y-axis and stress in the x-axis, you can see that the Young's modulus is constant until it reaches sigma naught, and then there is a sudden drop and it reaches the slope 0 when it reaches sigma y. So this again can be represented in terms of stress versus slenderness, where you can see that there is a deviation between the Euler curve and the curve that is shown in the cyan color. That deviation is represented by the point, red color point, and the slide on the right hand side. And this graph, which is parabolic in nature between sigma y and the red color point, is given by this tangent modulus theory. However, tangent modulus theory does not take account of the fact that I columns buckling about the minor axis are weaker comparing columns with the same slenderness ratios due to more unfavorable distribution of residual stresses. Nevertheless, column design curves based on the above approach were widely used before the introduction of the more recent multiple column curves approach. According to Shanley's concept, axial load and bending stress increase simultaneously after the critical load has been reached, and no strain reversal occurs as the member begins to buckle. For a steel column, the absence of strain reversal at buckling means that only the elastic part of the cross-section contributes to the internal resisting moment of the deformed member. Based on it, one can conclude that the critical load in the inelastic range is given by the Euler load with the moment of inertia of the entire cross-section I replaced by I sub E, the moment of inertia of the elastic part of the cross-section. Basically, Young's modulus into I sub E is equal to tangent modulus into I. So, either we decrease the cross-section from I to I elastic, which is smaller, or we decrease the material from E to E sub T. We know that P critical equal to pi square E I sub E divided by KL square. So, dividing A on both sides, we have P critical by A equal to pi square EIE divided by A into KL square. We can multiply this equation and divide this equation by I. So, we have sigma critical equal to pi square E divided by A into KL square into I by I. But we also know that I equal to AR square. So, substituting I equal to AR square at the numerator, we have pi square EI by A into KL square into AR square by I. So, this A and A gets cancelled. So, we have sigma critical equal to pi square E divided by KL by R the whole square into IE divided by I. So, this IE by I is the reduction factor and it depends upon the residual stress distribution, the shape of the member, the axis about which the column bends. So, consider an idealized cross-section. You have this idealized cross-section where the parts of the flanges at the edges have yielded and the portion between the flanges is elastic in nature, which is shown by the hashed line. The assumption is the bending resistance of the web and the moment of inertia of the flanges about their own centroidal axis is negligible with the partially yielded flanges unshaded area. So we can see that the elastic region of the width of the flange is given by B sub E. The total width of the flange is B. The height of the section from center to center is given as H. The thickness of the section is T. Again, there is a strong axis bending, which is XX, and weak axis bending, which is YY. The yielded portion is solid blue, and the elastic portion is highlighted as hashed 1. So bending about x-axis, we have here IE by I equal to 2 into BE into T into H by 2 the whole square divided by 2 BT into H by 2 the whole square. The 2 represents the flanges at the top as well as the flange at the bottom, which can be represented as AE by A, which is the area of the elastic region by the total area. Now the bending about YY axis can be given as IE by I equal to 2 into T into B cube divided by 12 divided by 2 into T into B cube by 12. Basically, it is the minor axis bending. Again, we get the same thing, which is AE by A the whole cube. So letting tau is equal to AE by A, we have for strong axis sigma critical equal to pi square E divided by KL by R the whole square into tau. And for weak axis, we have sigma critical equal to pi square E divided by KL by R the whole square into tau cube. So the reduction factor is much larger for weak axis bending than for strong axis bending, and that each case will therefore have a different column strength curve. The reduction factor can be determined either experimentally by obtaining a stub column strength curve or analytically if the residual stress distribution is known. The stub column stress strain curve plot is a plot of strain versus average stress. So its slope is given as E sub t, which is the tangent modulus, equal to d of sigma A divided by d of epsilon. Sigma A is given as P by A and epsilon is given as P by A sub E divided by E. So this boils down to E into AE by A, which is equal to E into tau. So tau equal to E sub t divided by E, which is equal to AE by A. For strong axis, sigma critical equal to pi square E divided by KL by R the whole square into tau. For weak axis, sigma critical equal to pi square E divided by KL by R the whole square into tau cube. Letting n equal to sigma critical by sigma y, we have lambda equal to KL by R into 1 by pi into root of sigma y into 1 by R. Now what is lambda will be shown in the couple of seconds. So we have 1 by R is equal to tau for strong axis and tau cube for weak axis. So the relation between n and lambda is given as n equal to 1 by lambda square, as you can see here. So when we plot the non-dimensional version of the stress versus the slenderness, we have 3 different curves. The one with the blue is basically the Euler curve, and the one with the cyan color is the strong axis bending curve, and the one with the yellow color is the weak axis bending. Clearly, it can be observed that the one with strong axis bending has a higher strength curve compared to the one with the weak axis bending, and this is primarily due to the residual stress distribution that occurs in the wide flange shapes. Now, the reduction factor tau can be determined analytically using linear residual stress distribution. So we have a flange whose width is B and whose residual stress distribution is given below. When the average applied stress sigma A equal to P by A is above the proportional limit of the stub column, the cross section is partially plastic and partially elastic. This can be shown in the figure that is seen here. The solid portion is yielded part and the portion that is hashed is elastic. And the stress distribution is shown below. Sigma naught is the stress at the proportional limit. Sigma r is the residual stress and sigma y is the total yield stress. The total load P acting on the member is given by evaluating the above diagram. So here we have the total with B. The elastic portion is given as B sub E, and we can have this split into rectangular portions. As you can see here, P equal to 2 into sigma y into B minus BE into T, which is the two rectangles on the left and right side. And then we have a rectangle at the bottom plus 2 into sigma naught BE into T, plus we have the green colored portion which can be obtained by taking the entire rectangle and subtracting the bigger triangle at the center, which is given as 2 into sigma y minus sigma naught into BE into T minus sigma Y minus sigma naught into BE into T by 2. So we can simplify this further by expanding it. So 2 into sigma Y into A minus AE plus sigma naught into AE plus sigma Y minus sigma naught into AE minus sigma Y minus sigma naught into AE by 2. So we have taken the 2 outside common and we have got the resulting equation. This can be further simplified as 2 into sigma Y into A minus AE plus sigma naught into AE plus sigma Y minus sigma naught into AE by 2. Again, we can simplify this further by expanding it. So we have 2 into sigma Y into A minus AE plus sigma Y plus sigma naught into AE by 2. So this becomes equation 1. To simplify this equation further, let's take advantage of the similar triangles. As you can see here, the blue color similar triangles has a depth of sigma Y minus sigma naught. The yellow color triangle below has a depth of sigma R and the green color triangle has a depth of sigma R as well. So all of them have the curve theta here, which is the slope is the same in all the locations. Now the distance for the yellow color triangle is x1 and for the green color triangle is x2. Basically, these are all similar triangles here because sigma r is the depth on both sides. So x1 should be equal to x2. But we also know that x1 plus x2 equal to b by 2, which indicates that x1 is equal to x2 is equal to b by 4. So now from the similar triangles at the top, we have sigma y minus sigma naught divided by sigma r is equal to b by 2 divided by b by 4. This again can be simplified as sigma y minus sigma naught is equal to 2 into be by b into sigma r. So sigma naught is equal to sigma y minus 2 into sigma r into be by b. And this value can be substituted in the above equations, equation 1. So this can be further simplified as sigma naught equal to sigma y minus 2 into sigma r into ae by a. The ae by a is nothing but b by b into t divided by t. So if the width is now converted into area, so it becomes ae by a. So equation 1 now becomes p equal to 2 into sigma y into a minus ae plus sigma y plus, instead of sigma naught, we put sigma y minus 2 into sigma r into ae by a into ae by 2. So this becomes 2 into sigma y into a minus 2 into sigma y into ae plus 4 into sigma y into ae by 2 minus 4 into sigma r into ae by a into ae by 2. This again can be simplified further as 2 into sigma y into a minus 2 into sigma r into ae square by a. Dividing throughout the cross section with 2a, we have sigma a is equal to sigma y minus sigma r into ae square by a square. Sigma a is equal to sigma y minus sigma r into tau square because ae by a is equal to tau. So now sigma r into tau square is equal to sigma y minus sigma a. Tau square equal to sigma y divided by sigma r minus sigma a divided by sigma r. We have tau equal to root of sigma y by sigma r minus sigma a divided by sigma r. This tau is nothing but root of sigma y minus sigma a divided by sigma r. And we can again take sigma y from the equation inside. So we have tau equal to root of 1 minus sigma a by sigma y into sigma y by sigma r. So sigma a by sigma y can be represented as n, which is the ratio between the applied stress and the yield stress. So tau equal to root of 1 minus n into sigma y divided by sigma r. So tau equal to 1 minus n into sigma y divided by 0.3 sigma y because sigma r is typically taken as 30% of the yield stress. Note, the sigma r value can be anything depending on the residual stress provided. Here we are taking it as 30% of the yield. So tau equal to root of 1 minus n divided by 0.3. Here n equal to sigma critical divided by sigma y. And we know that sigma critical is equal to pi square e divided by kl by r the whole square. Let's say that it is equal to sigma y. So kl by r the whole square is equal to pi square e divided by sigma y. This can be further simplified as kl by r is equal to pi into root of e by sigma y. So kl by r into 1 by pi into root of sigma y by e is equal to lambda, say. So when we square on both sides, we have KL by R the whole square into 1 by pi square into 1 by E into sigma y is equal to lambda square. Now for strong axis, we have sigma critical equal to pi square E divided by KL by R the whole square into tau. This gives rise to the equation KL by R the whole square into 1 by pi the whole square into 1 by E is equal to tau by sigma critical. We can substitute this above value in the equation. Therefore, we get tau by sigma critical into sigma y is equal to lambda square. Now, we also know that n equal to sigma critical by sigma y. So, tau by n is equal to lambda square and n equal to 1 by lambda square into tau for strong axis and n equal to 1 by lambda square into tau cube for weak axis. So, here we can say that for strong axis, sigma critical is pi square E divided by KL by R the whole square into tau. This implies that n equal to 1 by lambda square into tau and lambda x now is equal to root of tau by n. So, lambda x represents the slenderness in the major axis or strong axis, which is given as lambda x equal to root of 1 minus n divided by 0.3 divided by n. For weak axis, we have sigma critical equal to pi square E divided by KL by R the whole square into tau cube. N is equal to 1 by lambda square into tau cube, which implies lambda sub y equal to root of tau cube by n, which gives rise to the equation lambda sub y equal to root of bracket open root of 1 minus n divided by 0.3 the whole cube divided by n. Increasing the value of n from 0 to 1, we can plot the column curve for wide flange shape with residual stress. So when we have this major axis buckling and we have minor axis buckling, we have two different slenderness ratios. So when we plot the normalized stress versus non-dimensional slenderness, so we have the strong axis curve which is shown in blue color. Then we have the weak axis curve which is shown in orange color. And we have this Euler curve which shows the dark blue color here. So the intersection between all the three is the point at which inelastic buckling begins to happen. To the right is basically elastic, to the left is inelastic. Now let's talk about the Column Research Council curve, also known as CRC design curve. So you can see that the CRC design curve is shown by the dotted lines that lie between the strong axis bending and the weak axis bending. The red line shown in the figure, which provides a compromise between strong and weak axis bending, was recommended by the Column Research Council in the second edition of its guide. So this gives a closer view of the CRC curve. The first part of the curve is basically the curve from Engelsser, which includes the tangent modulus pi square E sub t divided by L by R the whole square, which starts from A and ends at B. And then from B onwards to the right, basically it is a part of the Euler hyperbola pi square E divided by L by R the whole square. The x-axis is the slenderness L by R and y-axis is the compressive stress sigma sub c. So this is a standard parabola of the form y equal to ax squared plus bx plus c, which can be written as y equal to a into x squared plus b by a into x plus c. Adding and subtracting b squared by 4a, we have y equal to a into x squared plus b by a into x plus c plus b squared by 4a minus b squared by 4a. So we take plus b squared by 4a inside the bracket, we have y equal to a into x squared plus b by a x plus b squared by 4a square plus c minus b squared by 4a. It can be further simplified as y equal to a into x square plus b by a into x plus b square by 4a square bracket close plus 4ac minus b square by 4a. The first term here inside the brackets can be represented as x plus b by 2a the whole square. So the equation becomes y equal to a into x plus b by 2a the whole square plus 4ac minus b square by 4a. Upon comparing with the general equation of parabola, which is y equal to a into x minus h the whole square plus k, now we have two terms h comma k, which is the vertex given as minus b by 2a comma 4ac minus b square by 4a. This h comma k is the vertex and it is shown in the figure on the left side with the into mark, which is red in color, h comma k. The axis of symmetry for this parabola is given as x equal to minus b by 2a, and since it is along y axis, minus b by 2a is equal to 0, which indicates b equal to 0. So we substitute b equal to 0. In the above equation, we have sigma sub c equal to a into L by r the whole square plus c, where x is represented as L by r and y is given as sigma sub c. So we have two boundary conditions here. When sigma sub c at L by r equal to 0, we have sigma sub c is equal to sigma sub y. Similarly, sigma sub c at L by r equal to L by r p, which is proportional, we have sigma p. When we substitute the first condition, which is sigma sub c equal to sigma y at L by r equal to 0, we have sigma y equal to c. So we have the next boundary condition, sigma p equal to a into L by r sub p the whole square plus sigma y. This gives the constant a equal to sigma p minus sigma y divided by L by r sub p the whole square. This can be substituted in the above equation. We have sigma c equal to a into L by r the whole square plus c gives sigma c equal to sigma p minus sigma y divided by L by r sub p the whole square into L by r the whole square plus sigma y. So sigma c now becomes sigma y minus of sigma y minus sigma p divided by L by r sub p the whole square into L by r the whole square. Since sigma sub p is an intersection between the two, we have sigma sub p is equal to pi square e divided by L by r sub p the whole square. We also know that sigma y minus sigma p is equal to sigma sum r, which is the residual stress. From the equation, sigma sub p equal to pi square e divided by L by r sub p the whole square, we can determine L by r sub p the whole square is equal to pi square e divided by sigma p. So we can substitute L by r sub p the whole square in this equation above. We have sigma c equal to sigma y minus sigma p into sigma p divided by pi square e into L by r the whole square. We can rewrite the terms sigma y and sigma r by the following equation. We know that sigma y minus sigma p is equal to sigma r. Therefore, sigma y minus sigma r is equal to sigma p. So both these terms can be substituted. Thereby, we eliminate sigma sub p. So we have this equation here. Sigma c equal to sigma y minus sigma r into sigma y minus sigma r bracket closed divided by pi square e into kl by r the whole square. Although the maximum compressive residual stress in the flange of structural steel members is approximately 0.3 sigma y, a curve better suited to both weak and strong axis bending is obtained by letting sigma r equal to 0.5 sigma y. So when we substitute sigma r equal to 0.5 sigma y, we have sigma c equal to sigma y minus 0.5 sigma y bracket open sigma y minus 0.5 sigma y bracket closed divided by pi square e into kl by r the whole square. This can be further simplified by the equation on the right, and we get sigma critical equal to sigma y minus sigma y square divided by 4 pi square e into kl by r the whole square. We can divide both sides of the equation by sigma y. We have sigma critical by sigma y is equal to sigma y divided by sigma y minus sigma y square divided by sigma y into 4 pi square e into kl by r the whole square. So this gives rise to the equation sigma critical by sigma y is equal to 1 minus 1 by 4 into 1 by pi square into sigma y by e into kl by r the whole square. Letting n equal to sigma critical by sigma y and lambda equal to kl by r into 1 by pi into root of sigma y by e, we have lambda square equal to kl by r the whole square into 1 by pi square into sigma y divided by e. So now n becomes n equal to 1 minus lambda square by 4, and which gives rise to the value lambda equal to 2 into root of 1 minus n. Taking n equal to 0.5, because the residual stresses is 50% of the yield, we have lambda equal to 2 into root of 1 minus 0.5. This can be further simplified, giving the value lambda equal to root 2. Now when we plot the curve, the normalized stress versus non-dimensional slenderness, we have three different curves. The top one is the strong axis, which is blue in color. The bottom one is the weak axis, which is yellow in color. We have the elastic curve, basically the Euler curve, which is dark blue. And then we have the CRC curve, which is pink in color, as you can see here. So the CRC curve is a nice compromise between the strong axis as well as the weak axis strength curves. So this intersects at point root 2. To the right, it is elastic. To the left, it is inelastic. So we have n equal to 1 minus lambda square by 4 for lambda less than root 2 and 1 by lambda square for lambda greater than root 2. For strong axis, we have lambda sub x equal to root of 1 minus n divided by 0.3, the whole divided by n. And for weak axis, we have lambda sub y equal to root of bracket open root of 1 minus n divided by 0.3 bracket close to power 3 divided by n. So for n equal to 0.7, we have this cutoff point as 1.2, which indicates that to the right of 1.2 is elastic and to the left of 1.2 is inelastic when we consider the residual stress as 30% of the yield stress. So this CRC curve was first proposed by F. Blake in his book Buckling Strength of Metal Structures. Now let's look at the relationship between the shapes of stress strain curves and stress versus slenderness curves. The first curve is a bilinear stress strain curve. The second one is a bilinear stress strain curve as well as the residual stress effect on a stub column coupon, which is given by the dotted lines in red color. Basically, it is linear up to sigma p and it becomes slightly nonlinear when it exceeds sigma p and finally joins sigma sub y. The stress versus slenderness curve is shown on the third figure on the left. Here we have the cutoff point sigma y when it reaches the material limit and it cuts with the Euler curve, which is sigma critical. This curve represents the stress versus slenderness. The next two figures gives you the stress versus slenderness for major axis as well as the minor axis. You can see that the major axis is convex in nature and the minor axis is concave in nature. Basically, when the residual stress pattern is given as CTC pattern, it favors the major axis, and when it is for minor axis, you get a lower strength curve. With this one, we complete the understanding of residual stress patterns, and we will continue our conversation on stability in the next class. Thank you very much.